Okay, so last time, section 1.5, we started talking about quantifiers, or actually we didn't quite get to the quantifiers themselves. We were talking about these things called, excuse me, there was a question in the chat. I'll have to double check my dates, but I'm pretty sure I already fixed it. But like I said, I'll double check the due date on that one. So continuing, we didn't quite get to quantifiers. What we talked about last time were these things called propositional functions. And these are something like this sentence here. They look like propositions. They have the same kind of structure, but instead of having a single truth value, instead they have a variable in them. So like this one says n is an even integer, and it looks like a perfectly good proposition, but we don't know what the value of n should be. And the truth value of the proposition depends on the number. So for example, if you put in the number 1, this would be false because 1 is odd. But if you put in the number 2, then this would be a true statement because n is, or 2 is even. So we have this new idea of propositional functions that we talked about last time, and we finished this whole first page. Don't want to spend too much more time talking about those because we need to move on to the quantifiers. Oh, I guess one more thing I should remind you of since I'm about to say it again. The domain of discourse for a propositional function is very similar to the domain of any other function. It's the set of things that you can plug in. So for example, this proposition, since it's talking about integers, the kinds of things that you want to be able to plug in here would be integers. So the domain of discourse would be that set. And the set depends on the function. It could be different each time. Okay, so now let's talk about quantifiers. Let P be a propositional function like the one that we were just talking about with domain of discourse D. Then the statement for every x P of x is called a universally quantified statement. So what this quantifier is doing is it's telling you that this argument or propositional function is true for everything in your domain. And we think of the domain as our universe. That's where that word comes from. Like we had universal sets going back to the first section. And just write down what I said. So we're claiming, we're asserting that all of these are true no matter what we plug in for x. Okay, and just like all of the other ideas in logic that we've talked about before, we have symbols that we usually use in place of the English words to save ourselves some writing. And for this one, we're going to use this symbol. It's a capital A turned upside down, and it means for every. So it's going to take the place of these words here. So that means if I wanted to rewrite this symbolically, I could replace for every with the upside down A and write it this way. So we save ourselves quite a bit of writing. So instead of writing a whole sentence, we can just use a few symbols. Just write that statement down again. For every x, p of x. And the meaning of this statement is essentially what you would think it would be just from the plain English. For every x, p of x is true if whatever this proposition is, p of x, is true for every single x in the domain. In the domain of discourse, just write it all out. D and the opposite of that, in order to make it false, that would be if at least one of these is false. So not every one of them is true means at least one is false. For at least one value of x. And let's go straight to the examples, like this one. So just take a minute to look at the symbols, the symbolic way of writing this proposition, and try to think how you would translate this into English using our new symbol, the upside down A. So all we're going to do is, when we translate, replace this upside down A with for every. So for every x, and then this inequality, x squared is greater than or equal to 0. What should the domain of discourse be for this example? What kinds of things can we plug in to our inequality? X squared is greater than or equal to 0. It definitely needs to be numbers, right? Right, Curtis, real numbers. Because we can square any kind of number. Okay, and then the next question is this proposition true? So is it true that when I square a real number, I always get something back that's greater than or equal to 0?
Yes.
Right, this is definitely true. So remember, if I have a positive number and I multiply it with itself, we definitely get back something positive. If I have a negative number, then when we multiply it with itself, we have two minus signs, and those two negatives become a positive. So yes, this is definitely a true proposition. Are there any questions before we look at something else?
What is the name of the for every sign?
What is the name of it? I'm not really sure if it has a specific name other
That
than the this one. It's the universal quantifier.
oh, okay.
Upside down A works though. I think everyone will know what you're talking about. Okay, so the next thing I want to do is take a look at this little bit of pseudocode. Since most of you, or possibly all of you, are computer science majors, I think you probably already know what pseudocode is, but in case you need a reminder, this is essentially computer code that's written in English instead of a particular programming language. So these are basically instructions for a computer. And my little bit of pseudocode is this block of text over here on the right. So it has indentation that kind of works how computer code would work to tell you the structure. And then the symbols are defined over here, and we write out what they are in words instead of using code. P, which you'll find on this line, is going to be one of the propositional functions that we've been talking about. And the kinds of things that we can plug into our propositional function come from this set. So this is just a set of a finite number of things. Since whenever you're dealing with a computer, you always have to deal with some concrete finite set of things because, well, computers can't run an infinite amount of code. It would never finish. So our set just has n items in it. And maybe we can just read through this. For I equals 1 to n, or for I from 1 to n, whichever way you want to write it. If not p of di, so we're plugging something from our domain into our truth, we're plugging it into the propositional function to get a truth value, and then we're putting an extra negation on it. So we plug it in and then swap the truth value. If this is true, then my pseudocode is going to return false, and it'll stop right here. Otherwise, it's going to go back up to the for loop and move on to the next number in our list. So starting at 1, we go back to 2, and all the way up to n, just like a normal for loop. If we get all the way through the for loop, all the way from I equals 1 to n, and this is never true, then we're going to get to this last statement, return true. And that's where the program will end, with a true instead of a false. So first question, what does this program do? Can anyone tell? It's not an easy question.
I'm not quite sure what D is in this situation.
That's because I haven't told you. It's just something that we can plug into our propositional function. So it could be a number, or maybe it could be a string, just some letters. Could be anything.
It seems like the program's gonna run a bunch of times returning true or false.
Okay, so something that I should point out, I guess, is that once the computer actually runs one of these lines that says return, the program will finish. It'll stop. So if it ever gets a true statement here, it's going to get to this next line, return false, and stop.
Oh, so it's gonna return. Then I think it runs until it returns false then.
Okay, so it'll definitely run until it either returns false or true, but what I'm trying to get at is what would a false mean and what would a true mean? And it's a hard question. Let me just tell you. This program is going to determine if this proposition, the kind of proposition that we're looking at right now, is true or false. It's actually going to test whether this is true or false. So let's think that through just a little bit. So remember, if this universally quantified statement for all x p of x, if this is true, then that means every value that you plug in for x is going to give you back a true, because it's true for all values of x. So that means, going back to the pseudocode, this here, p of di, is always going to be true if this is a true proposition. So this is true, and we're adding a negation to it. That means this bigger set of parentheses is going to be a false every single time, no matter what you plug in. So that means the for loop is going to get to a false in this if, and then ignore this line, and then loop back through. So it'll plug in 1, it'll get a false, so it'll go back to 2, get another false, and then it'll just continue all the way through the end, and it'll never reach a true statement here, which means this line of code will never run. Instead, it's just going to finish the for loop and return true, and then stop. But if this statement is false, that means that there's some value that we can plug in to the propositional function and get a false statement here. So there's some value of I where we get a false. Then that false is going to get swapped by the negation to a true. And since we get a true here, the next line after the if is going to run. And the computer will return false. So that's a little complicated. I can't really write all of it down. Your textbook actually explains this a little bit. what I want to do, hopefully to convince you that that's what the code actually does, is go over to a handy Jupyter notebook with Python and actually run the code, actually write it out and run it. So Python is convenient because it looks a lot like pseudocode. Everyone should be able to read it, even if uh, even if you don't know how to program actually in Python. Let's see, maybe write a little comment. So we want to run the pseudocode. And for this particular piece of code, my domain of discourse, I'm going to make it pretty easy on us. It's just going to be the numbers up through, let's say, 10. And then I need to define a function. I'm not actually going to plug any variables in it, so I'll leave that blank. And now we can write the pseudocode. So I'll say for I, well, we can write it that way. The more usual way is to say for I in the range of 1 up to our stopping point 10, but I have to go 1 past that in Python. Don't really want to get into the technical reasons for that. And I also need to tell you what my propositional function is going to be, since we need to pick it to plug it in. And let's just do something simple. Let's just test to see if x is greater than 1. So when we plug in something, we'll just see if it's greater than 1. So if not that, then our program will return false. And otherwise, it'll return true. Okay, so hopefully no bugs crept in. Oh, like this one. So I'm plugging in the numbers 1 through 10, and that's what my for loop is cycling through. So this x should actually be the I from the loop. Okay, so if we didn't introduce any new bugs, will this return a true or a false before I run it? Anyone? Is my, oh, someone's saying something in the chat. Okay. False, right. Because the first number that gets plugged in is going to be 1 from my loop, right? And it's going to plug it in here to check to see if 1 is greater than 1, but of course that's going to get a false. So this function should return false, and it does. A simple change to see if this also works, if the propositional function is always true, we can change this strict x is greater than 1 to a little less strict greater than or equal to. And that should be a true. This should always be true, of course. 1 through 10 is always greater than or equal to 1. So if I change up that propositional function, then I should get a true. And that does work out. So if you wanted to try running this pseudocode in a different language that maybe you know, that might be a good little bit of practice for you. Does anyone have any questions over the pseudocode before I stop the screen share? Okay, so like I said, if you don't know exactly how to program in Python, that's not really a big deal. Probably you can just read it, and it's close enough to the pseudocode that even if you don't know the exact syntax, it's still understandable. And let's move on to this next example. I want to verify this proposition for every real number x. If x is greater than 1, then x plus 1 is also greater than 1. So what is, first of all, the domain of discourse? Can you tell from the proposition? Are there any keywords? Like these? So the proposition actually comes right out and just tells you what the domain of discourse should be. So x, whatever we're going to plug in, is always going to be a real number.
What's tripping me up about that is the the word discourse. Like I understand the domain, I guess. I understood. I
Uh-huh.
just thought I didn't understand, I guess.
So domain is what you would use in most math classes for the things that you plug into a function. When we're talking about logic, sometimes we say domain of discourse. Um, and if you just left off this word or these two words, you would be totally fine. Um, but in logic, we're usually talking in English or some sort of language. And this domain of discourse,
It's pretty much the domain of the problem.
right. And translating it into maybe more common English words, this would be like the topic of discussion. So if you looked up the meanings of these words in the dictionary, it would translate more or less to this topic of discussion.
Thank you for
Yeah.
breaking that down.
Okay. So the domain of discourse is the real numbers. And what I want to do, or what I already told you that we want to do, is to verify that this is actually true. So if I plug in a real number, I'm always going to get something true. So let's think about it. So what if I just picked a number? Um, well, this first part of the statement is going to be either true or false, right? So if I pick 2, this is going to be true. But if I picked 0, 0 is greater than 1. That's false. So we have to break down our verification into maybe 2 parts, where this is true and where it's false. Oops. So if x is greater than 1, um, sorry, I was pointing to the wrong spot. If this is true, then what I can do is just add 1 to both sides. Or I don't even actually have to add 1 to both sides. We can just say that if I add 1 to the left, we're getting a larger number. We're increasing its value. So it's still larger than 1.
You say, yeah.
Right. We don't even really need to check anything. The complication comes in if x is less than or equal to 1. Because that means this part of the statement, x is greater than 1, is false. What does that do for the conditional argument here? or conditional proposition, to use the correct word. So if this part of the conditional proposition is false, the first part, what does that do for the overall truth value? Right, Victoria, it's vacuously true. So if this part is false, it doesn't even matter what happens over here. It doesn't even matter if x plus 1 is greater than 1. So the conditional proposition is vacuously true. Good. So we've checked in both cases. It's true if I plug in a number that's actually bigger than 1, and it's vacuously true if I plug in something less than or equal to 1. And that takes care of all the real numbers. So we've checked for both of these. That means we're done. It's true. Any questions over that idea of breaking it down into two cases like that? Okay, so far we've been talking about the single universal quantifier, the upside down A. There's another quantifier that we need to talk about today. Again, we're going to let P be a propositional function with domain of discourse D. Then this statement, there exists X such that P of X is called an existential or existentially quantified statement. Fix the spelling there. Okay, so this one is quite different from the first quantifier. That was saying something for everything in the domain. This is saying something for a single thing in the domain. There just exists something. And for this one, we're going to use an E, a capital E that's been turned around backwards. So just like we flipped the capital A for the first quantifier, now we're going to flip the E. And this simply means there exists. And this will give us our shorthand notation like this. So this is how you would translate the sentence, there exists X, such that P of X, into symbols. And sometimes when you're leaving your propositional function sort of blank, like I have here, you'll use a comma instead of the words such that. And this also has its, plain English meaning. This is true if there actually is an X where the propositional function is true. So it's true if P of X is true for at least one X in the domain of discourse. And the opposite, the false negation of that, that sentence might have had too many negatives in it. The negation of this would be if p of x was false for all x, so it's never true. Okay, any questions about the new quantifier before we look at examples? Okay, so let's take a look at this first example. The first thing, whenever you see a symbolic proposition like this, the first thing that you should do is to try to translate it into words so that you can be sure that you understand what it means. So this backwards E means there exists. What should the domain of discourse be before I go on? What kinds of things can we plug into this equation for x? Right, real numbers. So when I'm translating it into English, I should include that piece of information in my words. So I should say there exists a real number x such that this equation is true. And then we can just copy it down. So x over x squared plus 1 equals 2/5. Okay, so in order to show that this existentially quantified statement is true, we have to show that the equation is actually true if we plug in a value. We need to find that value, is what I'm trying to say. That makes this equation true. And another way of saying that is we have to solve it. Can anyone see a solution without having to do work?
Yeah,
What'll work? What can we plug in?
2.
Right. So if you pay attention to how the fraction works, you can kind of see the answer without having to do any algebra. You see that x is on top of the fraction over here, and there's a 2 on top of the fraction on the right. So if you just pick x equals 2, that'll match up. And in the denominator, x squared plus 1, if you plug in 2, you'll get 4 plus 1, which is 5. So is this true? This existentially quantified statement?
Yes.
Yes. Okay, any questions? Okay, so maybe I'll just pause there for a second before I flip the page over. Okay, so we got some practice showing that one of these kinds of statements is true. Now let's show that this one is false. And remember, this will be false when the propositional function is false for anything that we plug in. So keep that in mind. So in this one, we have to show that the inequality is false no matter what we plug in for x. Okay, but showing that an inequality is always false is kind of backwards from the way that we normally think in math. So instead of thinking about the inequality this way, what I want to do is flip it around. So if this is false, that means if I change this greater than symbol to a less than or equal to, we should always get a true. And this is the way that we normally like to think in math. We like to show that things are true. So if we can rearrange it this way, that's pretty nice. And let me just walk you through how you might do that. So the domain of discourse is the real numbers. We're given that up here. X is going to be real. So I can start off by just saying if X is real. And then something that we know to be true is this: X squared is greater than or equal to 0. And this is enough to get me started, because I can add 1 to both sides and still get a true inequality. So x squared plus 1 is greater than or equal to 1. That's still true. And now I can divide through by this expression, x squared plus 1. Whenever you're dividing an inequality like this, though, it's important to double check that you're actually allowed to divide by x squared plus 1. And we are, because this is always going to be a positive number. We're never going to be dividing by 0. And it's also never going to be negative, because it's greater than 1. So that means I don't have to worry about switching the direction of my inequality when I divide through. This is what we end up with. 1 is greater than or equal to x squared plus 1. And that's exactly what we wanted. It's written in the opposite order. Here we said it was less than or equal to 1, and here we're saying 1 is greater than or equal to. But that's fine. It still means the same thing. So that's one way to verify that an existential statement is false by verifying that another statement is true. So this way of reversing your thinking between true and false is going to be an important tool as we move forward with more complex ideas. Are there any questions?
What number did you add to both sides on that step?
Oh, excuse me. I said it out loud and then didn't write it down. Add 1 to both sides.
All right, perfect.
Why is it less than or equal to? What would we make it a less than or equal to?
Okay, so we're trying to think about when this initial inequality is false. And this
Okay.
is going to be false if the left-hand side is either actually equal to 1 or it's less than 1.
Oh, okay. That's okay. That just solved all my confusion. Thank you.
Okay, good. Okay, so let's talk about these laws. So this name has come up several times already. De Morgan's laws for logic. They're going to tell us that these pairs of quantified propositions have the same truth values. And then we'll talk about it maybe a little bit after I write them down. The first one relates to putting a negation on the universal quantifier. So I put a not symbol outside for all x p of x. And this is actually the same as this next expression. There exists an x such that not p of x. And then the second law relates to the existential quantifier. If I put a negation on the outside, then this is actually the same as this next expression for every x not p of x. So just take a look at the pairs and compare them. This first pair, you can see that what happened was the negation symbol got pulled inside, so it was outside over here, and now it's inside. But in order to do that, the upside down A, the universal quantifier got switched to the existential quantifier, the backwards E. And then the opposite sort of thing happened down here. If we put a negation on the outside of an existential, that's going to get flipped to a universal, the upside down A, and you'll pull the negation to the inside. And the reason why this is called De Morgan's law is that it relates to the other ones. I can just write down maybe one of them over here on the right. So De Morgan's law, the one that we already know, told us that if we put a negation on the outside of an and, then we can distribute it, but we have to change the and to an or. like this. And these, for quantifiers, work exactly the same. You switch the symbol. In this case, you flip it, the and to the or in this case, change the A to an E, and then pull or distribute the negation to the inside, like this. And your textbook goes through a little bit of the details about why that works, but it's actually exactly the same. And you can actually work through that yourself if you go back to what the quantifiers mean and what their negations mean. So for example, the universal quantifier, remember, it's true if it's true for every x, and it's false if there's one value of x where the propositional function is false. So another way of saying that is that there exists an x where the propositional function is false. And that's all these symbols are saying. And you can go to the definition for this one, the existential quantifier, and work through that as well. But to finish off class today and finish off the section, we need to talk about the next example or two, maybe just one of them, since we only have 3 minutes. So here I have a proposition that says, every gamer loves Call of Duty. I want to write it symbolically and then find its negation. So the first thing we might want to do is identify the propositional function and maybe label it p of x. So in this case, we're saying that something loves Call of Duty, the video game, in case anyone was unsure. So x loves Call of Duty. Is the propositional function. And the domain of things that we are plugging in is the set of all gamers, because we're talking about every gamer here. Okay, so we're saying every gamer loves Call of Duty. So we're saying for all x, p of x. So for every gamer from our domain, x loves Call of Duty. What's the negation of that? Well, one way to think it through is just to go up here to the first De Morgan's law. If we put the negation symbol on the outside, then it distributes through, but we have to switch the universal to an existential. But what does that mean? Right, these are symbols. What does it actually mean in English? We're saying that there exists an x, there is some value that we can plug in, some gamer, where the statement is false. So x doesn't love Call of Duty. Okay. Let's see, are there any questions?